The universal patterns, the grand regularity of nature, the leitmotif of my book, is readily discernible. It is apparent in various spirals, such as a snail's shell, the scales of a cone, and tentacles of an octopus, and the walls of flowing water. It is also easy to spot similarities in branching patterns. A tree trunk branches out into copious twigs, just as a river forks into countless tributaries. In most cases, however, we won't notice the similarity between shapes until we collect data and analyze it. So we see, for example, that the main line of a district heating network divides into numerous radiator terminals in the same way as veins branch out into the many capillaries. In the same manner, we can spot the regularity emerging through time, for example, from the similarity between the rise of carbon dioxide levels in the atmosphere and the spread of new words in a language. Data of various kinds disclose that spirals, distributions, and growth curves have approximately the same mathematical form. Why is the grand regularity reflected in certain mathematical forms? Why is nature mathematical in the first place? Galileo described the meaning of mathematics as follows. Philosophy is written in this grand book, which stands continually open before our eyes, I say the universe, but cannot be understood without first learning to comprehend the language and to know the characters as it is written. It is written in mathematical language, and its characters are triangles, circles, and other geometric figures, without which it is impossible to humanly understand a word. Without these, one is wandering in a dark labyrinth. In the early 1960s, Eugene Wigner, the Nobel laureate in physics, expressed amazement at how effective mathematics is in science. A mathematical presentation of one phenomenon often leads to a stunningly accurate account of the whole set of phenomena. Richard Hamming, the pioneer in information technology, in turn argued that we interpret the world in mathematical terms in order to see what we are looking for. Hermann Weyl, German-born mathematician, theoretical physicist, and a philosopher, was convinced of the same simplicity in the early 20th century. He said, "I'm bold enough to believe that the totality of the physical phenomena can be derived from a single universal law of the highest mathematical simplicity." The thermodynamic theory asserts likewise. While numerous processes are complicated, the general principle of nature is nevertheless trivial. For the ancient Greeks, geometry meant measuring terrain. The whole universe, too, has a shape. Although we might never find out why the substance is geometrical, string-like photons, we may learn what the essence of mathematics is. Let us take a concrete look at mathematics, for such a standpoint may help us to see something that might have escaped our notice. Edmund Husserl, a one-time student of the mathematician Karl Weierstrass, extolled Galileo's method, which parses an experience or an experiment into an equation. After this mathematization, a theory cannot acquire new ingredients from reality, because mathematical equivalence ensures that the theory is closed. So the panorama of reality through the lens of a theory cannot alter, even if we were later to find in the equations previously unnoticed implications about reality. For example, Hugh Everett discovered that quantum mechanics implies parallel universes, and Weyl found that general relativity entails wormholes. There is no way to mend a mathematical theory when it fails to tally with the data. Additions to the equations only degrade the theory into malleable model. The way out of the discrepancy is to mathematize experience again into a new law. That is what we did. We mathematized the experience of time passing into an equation of motion of quanta. In the revision of the worldview, the new wider vistas of reality arise from outside the formulas that the physicists of each era deemed to be the essence of their discipline. Even if language can be abstruse, as mathematics often is, there is no reason to believe that a clause invariably holds a negative wisdom. Then again, a simple equation can carry a great deal of truth. For example, it is no coincidence that the geometric square, such as in Einstein's formula E = mc squared, and those well-known squares of the Pythagorean theorem, is found in many equations of physics, for example, in Kepler's laws. The square is the Euclidean norm, in a sense, the optimum. For instance, mass is the comparison of a particle's curvature to the void's flatness, the ultimate reference. That is how we read mathematical notation. Whatever we equate had better denote a true balance. Otherwise, we would violate the equal sign, the foremost among the symbols of math. The solid basis for conservation laws in physics is the constant number of quanta rather than energy. The mathematics of modern physics has been studied over and again to uncover even the most extraordinary insights, such as superposition, entanglement, and non-locality. When physicists tell you from the mathematics of quantum mechanics that a particle goes simultaneously along two or more distinct paths, one struggles to swallow the story. Similarly, when physicists spell out from the mathematics of general relativity that the passage of time is an illusion, or that an object shrinks as it moves fast or is hit by a gravitational wave, one's intuition raises a red flag. Without math, we would not have these strange images, let alone delusions.
What equates with change?
When we know how to read mathematical notation, we can relate an equation to reality in the same way as we relate a sentence to its meaning. For example, the famous Navier-Stokes equation describes a variety of flows from a steady stream to a raging torrent. We can infer from the formula, as there is no general solution to it, that the course of events can be capricious, chaotic, turbulent. Plane geometry corresponds to balance because there is nothing more even than a plane. The Pythagorean theorem expresses this. For example, the arc length of quarks in the electron, neutron, and proton are squared in proportions of 3, 4, and 5. All matter can thus transform into the plane of the void as the universe attains perfect balance. In contrast to the Pythagorean theorem, there is no integer solution for the equation of non-Euclidean geometry. For example, a to the power n plus b to the power n equals c to the power n when n is larger than 2, according to Pierre de Fermat. In 1637, the French mathematician noticed down in the Diophantus Magnus Opus of Arithmetic that his marvelous proof, unfortunately, is a bit too long to fit into the margin of the page. That might be so, as the first valid proof assembled by Andrew Wiles and published in 1994 is 400 pages long. We can make sense of Fermat's last theorem too by plotting the equation with increasing values of n. Then we see that the shortest curve, n equals 2, is the ellipse. It is the optimum. For example, a planet on its elliptical orbit is in balance. At the optimum, the number of constituents is fixed, and hence the system is divisible evenly into its parts. The essence of Wiles' proof is that the ellipse is divisible by an integer, whereas the superellipses are not. The ellipse is a periodic despite its continuity because any point on the perimeter is both a starting point and the corresponding end point. Unless a curve comprised of parts divides evenly by an integer, it remains open and spirals outward like a nautiloid. This is how ancient Greek inferred the link between mathematics and physical reality, arriving at the conclusion that the substance is periodic, atomic. Is that the sufficient reason for the enigma that the mathematics make so much sense of nature? The connection between a change in geometry and a break in symmetry is tangible when the structures are known. For example, when the electron torus opens up and one of its loops, a neutrino, breaks loose, the W- boson emerges. In general, whenever a gap is introduced into a closed curve of quanta, symmetry breaks and curvature alters, that is to say, mass changes. Specifically, the renowned Young-Mills mass gap problem links the mass with symmetry so that the photon wave and a neutrino loop cannot transform from one to the other smoothly, that is continuously, without a gap, but only by opening and closing. The wireframe models of particles also show what kind of rotations, reflections, and reversals leave the structures as they are. These operations that change nothing define a symmetry group. On the other hand, the standard model of particle physics says that the massless particle cannot be torn asunder. The photon is eternal. On the other, modern physics concocts virtual photons that exist only for a fleeting moment. The fact that virtual particle model is used solely for calculation does not cure the inconsistency. If the calculation does not correspond to reality, what's the point?
What is math telling us?
It is often the case that a matter is understood only when the words to express it has been found. Likewise, a theory is not clear until its mathematical form is at hand. Darwin's tenet, the narrative about the survival of the fittest, remains somewhat abstruse until expressed as an equation of evolution. However, a mere equation can also be ambiguous in its meaning. Planck discovered the quantum from an equation, but it was Einstein who suggested that Planck's law is about the quanta of light. Likewise, Dirac found the positron from another equation, but it was Weyl who suggested that the second solution of the Dirac equation is the electron's antiparticle. The positron, that is to say. Dirac himself thought it was the proton. In mathematics, there is no room for interpretation, albeit none for error. It's a different thing to interpret mathematics as reality than to rationalize reality in mathematical terms. When deriving the thermodynamics from one's own experience, it becomes apparent that Planck's constant does not mean the quantization of energy, but rather the invariant measure of the quantum. Moreover, the two solutions of the Dirac equation do not mean point-like particles, but the tori of quanta, the electron and the positron. In any case, mathematical reasoning keeps the theory within its postulates. An alternative view therefore requires different foundations. Rather than considering a falling apple, Einstein inferred that if he were to fall freely, he would not sense gravity. Only after the mathematical form for this insight was found in Riemann's non-Euclidean geometry could Einstein test his thesis. The idea of the free fall seems to ring true, doesn't it? However, no one is truly free from the gravitational field of the expanding universe. Without the formalization of general relativity, it would have been difficult to notice that the observations, particularly on a galactic scale, does not match Einstein's intuition precisely. Mathematics makes our doubts more definite than mere words. If Schrödinger had not put his model of matter wave into mathematical form, we would have no specific object to doubt. Now we have, for we can find a solution to the Schrödinger equation in which time does not exist at all. The famous formula models an endless circulation. But the world is constantly changing. The wrinkles on my face are all too real. I've lost quanta irreversibly. Likewise, the flow of time must be put in the form of an equation. How else could we test whether Parmenides' idea of the indivisible element is correct? Quantum mechanics is a model of periodic motion, such as that of the quanta that form the electron. The circulation can be in any phase so long as we are free to define the point of observation. This randomness is neither strange nor unique to microcosm, let alone evidence of entanglement or the multiverse. What the second hand is pointing at when you take a glance at your watch is similarly arbitrary. When mathematics is not properly cognized, the equation can be even misunderstood. Particles are imagined as being virtual or envisaged as excitations of the vacuum fields. Without mathematics, we would hardly think about such oddities. Then again, the exactness of mathematics forces us to judge modern physics either as real, all the way up from its foundations, or as unreal all the way down to its roots. Even though the world changes, the steady state is held to be the norm of physics. That is why stationarity is known in precisely defined terms such as equilibrium, conserved, commutative, computable, linear, Euclidean, and deterministic, whereas the full range of processes is referred to by vaguely understood terms such as non-equilibrium, non-conserved, non-commutative, non-computable, non-linear, non-Euclidean, and non-deterministic. Plane geometry, familiar from school math, is a special case, for we live on the curved surface of the globe. Gauss not only studied non-Euclidean geometry, but considered that the space itself is curved. It is said that in 1820 he climbed on the three mountains Hohenhagen, Brocken, and Inselberg in central Germany and measured the adjoining angles of the three peaks. Their sum was 180 degrees. Light travels in straight lines. The Earth's gravity is too weak to make a visible difference relative to the free space. But the idea of curved space stuck. In 1854, Gauss' student Bernhard Riemann formulated a curved geometry, and Einstein adopted it as the mathematics of general relativity. The Einstein field equations that delineate how space-time curves about a celestial body are derived from the Einstein-Hilbert action using Lagrange's stationary rather than Maupertuis's evolutionary principle of least action. The German mathematician David Hilbert, unmatched in many areas of mathematics, worked on general relativity and had a hand in quantum mechanics too. Modern physics is thoroughly mathematical. It's mesmerizing, but sophistication does not make its import real. Big words do not make a tale true either. Have physicists lost their touch with reality on their way to the world of mathematics?
What is solvable?
In school, we are taught that probabilities always add up to 1. This unit norm is also the criterion for the solution of the renowned Riemann zeta function. This condition of balance is the natural way to prove the Riemann hypothesis, for the zeta function occurs in many models of stationary systems, such as nuclei, crystals, and synchronized systems called condensates. Leonhard Euler figured out how to write the zeta function as a product of its factors. His formula associates a prime with each state of balance, and hence these zeros are unique, non-trivial. Finding a new prime is as surprising as the emergence of a new compound or a new species. This analogy may appear unwarranted, but as Marcus de Sauté, a professor of mathematics at Oxford University and a well-known figure on BBC TV, says, primes are the atoms of arithmetic. Since the 1950s, the largest known prime has stepped up almost in a power law manner. This trend is also consistent with thermodynamics. We can therefore presume that it is not possible to predict the primes, not even from the condition of zeros of Riemann zeta function. There is no algorithm for finding primes because the search for factors changes the search itself. A newly found prime will be a factor of yet greater numbers. This conclusion is also propped up by the fact that the first digit of primes like that of the numbers in sequence, is 1 in about 30% of cases and 9 in less than 5% of cases. According to thermodynamics, numbers do not exist until they are given a physical form. From this perspective, reality is defining mathematics rather than mathematics determining reality. John Wallis designated infinity with a number 8 tipped over. The English mathematician needed a concept of infinity when pondering the age-old problem how to form a square with an area equal to that of a circle. In 1655, Wallis squared a circle with an expression of integers extending to infinity, from which pi can be approximately calculated. As is well known, pi is not a ratio of two integers. The discovery of such an absurd, that is to say, irrational number was a shock to the Pythagoreans. It implied that the substance is not divisible into elements, but rather continuous. Even though Newton invented differential calculus based on continuity, he did not consider a curve continuous, but rather points in motion. Differential equations, such as the Navier-Stokes equation and the Newton's second law of motion, are convenient to analyze, but the substance is, after all, divisible into indivisible quanta. Water feels continuous, but comprises water molecules. A stream of light seems continuous, but consists of photons. In the well-known story, Achilles is supposedly never going to overtake a turtle, as the turtle will always draw a little forward in the interval when the Achilles sprints to get to the point where turtle had just been. Although a distance could be divided infinitely in this way, the total length remains finite. Shortening the step size of a calculation without limit below the quantized reality leads to conceptual problems of continuity and infinity as encountered already by the ancients. Of course, Achilles will catch up with the turtle. Likewise, matter will stop being squeezed endlessly in the abyss of a black hole. But in quantum electrodynamics, distances are deemed to diminish without any bound, and hence interactions increase without any limit. One ought not to divide by zero. Well, this is acknowledged and dealt with by mathematical renormalization, but many scientists think that there must be a more realistic way. Dirac was frank. This renormalization is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it turns out to be small, not neglecting it just because it's infinitely great and you don't want to have it. As long as we realize that the vacuum quanta do not shrink unrestrictedly around the finite particle, quantum field theory works fine as a model of the void. Neither do the particles in a black hole contract endlessly, but unwind into the quanta of the void. The quantum itself is the constraint that prevents calculations from running off to the infinity. Renormalization is obsolete, for the quantum is, under all circumstances, equal to Planck's constant. Physicists are also flummoxed why the vacuum energy density is in reality 10 to the power 120 times lower than the value calculated by the standard theory. Such an error is made because the standard theory allows energy to increase to infinity over an infinitely short distance. It's clear that this cannot be true. Since modern physics is short of substance, the calculation is terminated at a theoretical length, Planck length, whereas the quantized particle and the vacuum impose the actual limits. Planck's units derive from the properties of the free space, all right, but when without understanding the structure of the vacuum. When difficulties stem from the foundations of a theory, they cannot be overcome within that theory. In historical perspective, the fundamental problems of science are not mathematical problems. It is the foundations of science that are problematic. At the end of the 19th century, some foremost physicists thought that particles are ether vortices. The issue with this view was that there could be too many kinds of vortices. Present-day physicists imagine that particles are strings, but the issue is that there could be too many kinds of them. The theory of supersymmetry in turn does not seem to match measurements, and the theory of inflation is in trouble because it lacks ways of falsification. As a general rule, the more obscure the basis of a tenet, the wider its spectrum of conceivable worlds. By contrast, the ancient atomism, now in the form of the quantum as the fundamental element, constrains our imagination of reality by spelling out the facts that could not be otherwise, the truths of nature. Mathematics governs modern physics for good reasons. The equations lay out unambiguous tests. Then again, mathematics imprisons physics with its problems when it is insisted that the new thinking must be mathematically equivalent to the old. Most notably, evolution does not fit into the equation of equilibrium. A theory's fruitfulness should be judged not only against observations and measurements, but also by studying the message itself, especially in its mathematical form. It is precisely mathematical analysis of modern physics that has led us to extraordinary conclusions. In quantum mechanics, the order of cause and effect can be swapped in an experiment that seems to display action at a distance. While such calculations agree with the data of stationary state, the conclusions are nevertheless strange, since the world we know is evolving.
How to model reality.
One tends to walk the length and breadth of an unfamiliar supermarket. A traveling salesman faces a similar problem. This is one of the Millennium Prize problems that the Clay Mathematical Institute listed in 2000. Curiously enough, there is no algorithm to work out the most inexpensive travel plan for the salesman from one city to next and finally back to their hometown. Nobody stands a chance at solving the problem because the calculation changes as it is being conducted. When the salesman arrives at a city, the number of cities that are still to be visited decreases by 1. This affects the optimization of the remaining route, and so on. In the worst case, the cost of each conceivable travel plan must be evaluated all the way to the end point, and hence there is no effective rule for the calculation. Problems are wicked not only because complexity, but also because everything hinges on everything else. Even problems involving only 3 bodies are unsolvable, as the motion of one body, say the Earth, affects the forces that act on the other 2, say the Moon and the Sun, and vice versa. Although the trajectories of bodies are unpredictable, not just anything can happen, as only those paths for which there are free energy can be taken. In the mid-18th century, Thomas Bayes reasoned that the present follows from the past in the same way as the latest judgments follows from previous perceptions. The English Reverend's idea of conditional probability was radical compared with the concept of static probability that Descartes and Fermat formulated for gambling. Bayes understood that knowledge accumulates from subjective interferences. Objective reality is not only unknown to us, but it does not exist. In other words, it's not only hard in practice to find out all necessary minutiae, but perfect knowledge is even in principle impossible because the act of knowing changes the object to be known. Today, artificial intelligence uses Bayesian probabilities to model alternative courses of events, but without comprehension of causal connections. Neural networks produce output by correlating input with the input from a training set, whereas we relate what we see with what we have experienced. We have learned to link causes with consequences the hard way. Likewise, only when a robot is made to blame itself for bad decisions will the responsibility of free will affect its decision making. It is fashionable to use so-called Markovian chains to simulate courses of events as if events were coincidences, whereas in reality, events lead to further events. Consequently, without causal connections, the simulation does not find its way to the balance, but must instead be steered into the predetermined final state. In other words, even a perfect match with the data does not make sense of the data. The mathematician Alexander Lyapunov from St. Petersburg, a good friend and a colleague of Andrei Markov, understood the least time nature of balance. The further the system veers from balance, the faster it will eventually move back. We should thus expect the forces of nature at a global scale shall strike back all the more fiercely the further away we perturb the planetary balance by our way of life. At worst, we might have already passed the point of no return, whereafter unprecedented forces are brought forth. The Millennium Prize problems are famous, but the fame does not automatically signify the genuineness of a challenge. Perhaps it is just difficult to free ourselves from persistent but misleading patterns of thinking. How do we learn to ponder differently? The answer may well require departing from prevailing preconceptions. A layperson finds many a mathematical problem unimaginably abstract. In turn, a mathematician might find it unthinkable that a mathematical problem could have a real-world counterpart. And yet, it may be precisely the concrete correspondence that helps us to puzzle out, for example, why the traveling salesman problem cannot be solved, and to realize that many other issues cannot be settled likewise. The wordings of Hodge conjecture, for example, one of the Millennium Prize problems, may seem at first glance incomprehensible. The essence of the conjecture is nonetheless plain. A system comprised of subsystems adapts to the surrounding systems, and concurrent changes in the subsystems lead to the changes in the surrounding systems. For instance, a community of people adjust to the natural habitat so that the changes in the habits go together with the changes in the habitat. An ecological niche is both produced and occupied. Likewise, an electron and the surrounding void make up an inseparable pair, a so-called dual, where one is affected by the other. In contrast to this physical realism, Dirac reasoned from Maxwell's equation that the dual of the electric charge would be the magnetic monopole rather than the void. Similarly, physicists consider today whether dark photons could be the dual of dark matter, since for them the vacuum is vague and its dual, matter, is murky. We think of science as a study of nature, but in fact it merely produces interpretations of reality, often based on mathematics. Such inferences are not solely founded on the observations at hand, but mainly on our previous conceptions or misconceptions. Sometimes it is thus more profitable to study our reasoning per se than to go on with studies based on our reasoning. Often, new thinking is dismissed by saying that extraordinary claims require extraordinary evidence, but the same mantra should then apply to instituted thinking. For instance, we have no evidence to back up the extraordinary factoids of entanglement, wave function collapse, action at a distance, space-time, dark energy, dark matter, cosmic wormholes, or multiverse. All we have is mathematics interpreted as if it was real. Mathematics is a formalism akin to a natural language. It describes events with astonishing accuracy, quantum by quantum. The precision is necessary to account for all causes and effects. When we understand reality as it is, we also recognize those mathematical models that are unreal. The reality check of ground-laying science is about realizing that modern physics is only a mathematical model of data rather than authentic account of reality.